my job as a technical director in IBM, what does happen? I don't know. Oh, I need to recheck to be sure then we are registered. I think it's okay. Yeah, it is. It's done. It should be done. Oh, I need to reshare it. Sorry. Yes. Yes. Again. Okay. Then yes, as a technical director in IBM and in charge of quantum computing for a vast majority of Europe and other markets globally, my job is to find people that will help us to build the best quantum computer in the world, enabling technology, software stack, etc., and find people that will take advantage of the tools that we are building, because at the end, if no one is able to use a quantum computer, we will have just spent a lot of money for nothing. That's the sad reality of the science. Then 20 minutes, yes, 20 minutes, 25 minutes to add very briefly some part of the strategy of IBM Quantum, where we add what we have done and what some of our partners have done. In short, does it work? It should. It doesn't. It is. 2 missions in IBM Quantum. The first one is what we will discuss today. The second one is what another important point, even if the quantum relevant cryptographically, the cryptographically relevant quantum computer is absolutely not there yet. That means that every buzz that you see on the market that someone had factorized a huge number with a quantum computer is pure bullshit. And that's, we don't see the risk right now, while the risk for the quantum safe stuff will happen for sure. That's one of the major use cases that all our friends from different military organizations are working on. Then for sure it will happen. If we think at IBM Quantum, what's the formula to make the world, let's say, to bring useful quantum computing to the world? That's the first mission. 5 standpoints. The first one is keep giving to the market what we call utility scale quantum computers available. That means that real tools, real quantum computers that are absolutely not perfect, but that could be used to make the algorithm world and the hardware world evolve. Whatever is the reason, from a quantum error correction point of view, quantum error mitigation point of view, pure hardware, pure algorithm, we need tools to test the methods and not only apply toy simulation model. Because at the end, you learn much more when you do something at scale, and that's what we have learned in the classical spaces too. You know, the question 20 years ago, or maybe more, 50 years ago was, what can I do with 1 megabyte of storage? And today we don't care anymore because we have plenty of storage. That's the same question on quantum computer. What can I do with, if I give you today 156 noisy qubits? Something useful, something that will beat classical computing? Of course not today. Something that will approximate the best approximation methods on the classical computing? Maybe yes, on some specific use cases. And that will make the overall progression of the world. Second point is, yes, we try to do and to say what we will do and to do what we have said, sometimes with some corrections because we don't have a crystal ball. We just try to publish and be very transparent in where we stand and what we do and what was published. Third point is that you cannot do anything in the quantum world alone. That means that we strongly believe in the ecosystem, we strongly believe in the strength of the ecosystem, and we are not experts in everything in IBM, absolutely not, especially from an algorithm standpoint. We know how to do maybe the best qubits in the planet. I would say maybe, because I'm sure that a lot of people will say, no, I can do better on that, then maybe. But we are not the specialized on every use cases from every customer, and we are not the specialized on every algorithm point of view. And if you just think alone, there is no management on that. Fourth point, we are committed to open source in IBM, and I will encourage you. That was an ask from the French government in June, they ask me the question, but how can I be sure that IBM is committed to the open source? Because on open source code, there is a risk that you will move away with all the open source code. First, if you have adopted that IBM will be committed to open source, you can imagine that if we do something very bad with Qiskit, I'm sure the community will create a fork and will say Qiskit_IBM is a hassle, and that will be fine. That's the beauty of open source. We do not own the code. We do not own the way people contribute to the code. And then at the end, that's why we believe in that. But why also we believe in that? Because we believe that we do not want to be stuck with one software applied to one hardware. Otherwise, there is a risk of a monopoly. And with a monopoly, there is a strong risk of no market. And we need to create a market because we are an enterprise. Then yes, at the end, we want to make money on quantum computer for sure. But if we are the only one able to make hardware that works at scale, there is no market because we will be regulated, blah, 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 etc., etc. That's why we are committed, let's say, very committed to open source. But there is also a lot of projects that we are handling on open source. And I think it was 5 to 6 years ago, we just acquired Red Hat. And Red Hat is still open source. And Red Hat is an IBM company, yes. Does it mean that Red Hat community moved away from everything on open source? Absolutely not. And all the community stuff are still there. But yes, for enterprise, we make money with Red Hat. And Quantum Safe, I already talked about that. Then, marketing chart. But just for everyone, quantum computing could be used in a lot of use cases. Then you will have all the charts, then I will not deep dive on that. The question is on which algorithm and at which time scale. And that's the one of the main question is when we work with customer, we do a maturity assessment. Okay, what is your dream and what can I really do right now? And sometimes there is an over expectation on quantum computing, which is quite large because people believe that we already can work with the large scale fault tolerant quantum computer, which is absolutely not the case. Then yes, some stuff on other use cases. And let's say, we strongly believe in two stuff. The first one is modeling chemistry in any sense, and modeling what happens at the quantum level of the materials. And second stuff is find hidden patterns. It could be on machine learning. We strongly believe that optimization will be mature before machine learning, but we are also working on machine learning. And I think the presentation we have by Alexei this morning was very strong on what could be the objective on quantum machine learning. And if you have doubt that there is money behind that, that's the BCG charts with all the billions value, blah, 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 blah. I don't know if it's real or not. What is sure is that on some market, there is a risk to be flushed out if you do not embrace any new simulation tools. What is it? I mean, it was the PDE on a classical CPU that makes the simulation of airplane much more easier and accurate in the 70s and 90s. And then maybe tomorrow it will be PDE with, quantum PDE, and some of our partners are working on that. Okay, IBM, short. Out time, 7 minutes. I'm good. The roadmap. I won't deep dive in the roadmap because first I don't have time, and then Jean-Michel will kill me after that. Then it's not feasible. What I want is to give you some trends. Bottom, and let's say how to read it. Bottom is the innovation roadmap. It's something that you will not see on the market. It's some proof point that we use internally to demonstrate that we have a viable path to create the development roadmap, which is what we sell to customers. Then that's why we demonstrate, to give you an idea, that's why we demonstrate Condor. Condor is 1,121 qubits in one fridge, and the quality of the qubits was not that good. It was at the same level of Eagle 2 years ago. Then the reality of that was just a pure scalability demonstration. And for example, I'm always cautious when I see some people saying they would scale to millions of qubits on one chip. To be very honest, I do believe that we are at the state of the art, and we demonstrate that we are at the state of the art in mates of how to make supraconducting qubits. And I don't know how they will scale 1 million supraconducting qubits on one chip. That's from a fabrication standpoint, I mean. And that's also the same case from a cabling point of view. 1 million supraconducting qubits mean the cable associated to 1 million supraconducting in one bridges. It will be a very large bridges. And then there is a lot of issue on that. That's why we move to another kind of, let's say, scalability and the way to scale in our roadmap. And after that, the colors is software, different kind of software. This morning in the introduction, we talk about the framework and the way to code and the way to implement. And I think that's something that we put a lot of effort in IBM. It's what we call the quantum-centric supercomputing. It's like HPC plus quantum computer, or it's like CPU plus GPU plus QPU. And in the QPU, we use FPGA. Then sometimes it's CPU plus FPGA plus QPU plus GPU. And at the end, that's much more heterogeneous computing. And which part of your computing you are putting on which part of and which kind of hardware. And that's a very strong question, and that's not an easy question. And after that, there is a use case at the end. One point on the hardware, people talk a lot about that, scale, number of qubits. Some people talk about quality. Yes, I got good quality qubits. And I think it's important to remain that 1 or 2 qubits together on one chip is not a world record if you can only do this world record in quality with 2 qubits. The question is, how do you maintain the quality while continue to scale? And third point, that's not a lot of people is talking about, is speed. Just look at the speed of to apply gate on some ion-based or other kind of methodology to produce qubits, and you will see that there is a bottleneck that some people want to hide for obvious reason. That's why we choose supraconducting, if you ask me the question. Scale, quality, speed. And if you ask me the question also, because we have a strong history in making chip. That's the reality. We are a chip making company. Then figure of merits of Ferron, you will have that. We are very proud of Ferron. It changed the market. That's the new chip. Figure of merits on the software side from a speed point of view. You can see the Gen 3 runtime. That's mainly software, but also hardware. And how we encode the FPGA. Future coupling, rather than having one chip with a large number of qubits, it's easier in our point of view to have smaller chip connected together. That's chip-to-chip connection, but close. That's long-term, long-range coupling. And we have internally and publicly, it will arrive in a moment of months. The Nighthawk, we changed the lattice, and I think that's very important, especially in optimization use cases, because it diminishes the number of gates and the number of swapping gates that you need from moving from 1 qubit information to your peers, etc., etc., etc. That's the kind of very important stuff. Then 4 degrees. And if you are very interested in that, I put you a chart in what does it mean on a trick, but what does it mean also on a real LUCG circuit in terms of reduction of the depths. Qiskit, I said that we remain committed to Qiskit and open source, and we will remain. We are very proud of the 74 survey in 2024. The survey will run by the Unitary Foundation in the following weeks, in my opinion. It will be in October. Please run the survey. The more people are using the survey, using the survey, the more accurate it is. But Qiskit is not only the SDK. It is, of course, the SDK, but it is also some other plugin. And we are, for example, very proud of the work we have done with Pascal, Riken, and other people. RPI on the Slurm quantum plugin. Slurm is a lot, I mean, it has a lot of usage in HPC world, in close combat with the software IBM tools called LSF, and both works. And it's how we can manage different kind of resources internally, but I will come back to that. Another point we are very happy is the way the Qiskit functions catalog work. I don't know if you have seen that, but IBM is providing to some software startups classical computing and help to work on the quantum computer to develop their own and to publish their own function on the kind of Hugging Face like. Then we do not own the IP, we do not take money on that, on their behalf. I mean, they are selling their IP and that's great. And I want to focus on some of them, which are the application one. Let's forget the chemical one, but the QPU and Q-control just publish and some very nice optimization software, as in. Then what I could encourage you is to have a look at these three functions from ESK, Q-control and global data and QPU, Q-control and global data, and to look at the documentation online that will give you idea of how they implemented a kind of max cut something solved with a quantum computer at scale. I mean, the optimization solver of Q-control, but I'm sure they will do, I don't know, are they doing a talk today or tomorrow? I forget, Q-control. Or I've seen them in the participant list. Maybe that's that. And the work they have done, that's pretty amazing. Is it at scale to fight with the classical? Maybe not. I'm sure that my friends of Cplex in IBM will say that Cplex is still better. But we are beginning to be close on that one. Then, tomorrow, from an hardware standpoint, I'm still good on the timing. We will, and we have published stuff on the fault-tolerant quantum computer. Then that's the timing and the different milestone. Loon will be a 6-way connectivity and a C-coupler demo this year. Kookaburra will be a long C-coupler and real-time decoding, blah, 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 etc. And we move around. And to give you an idea of the complexity, does it mean does this change from what we have today in terms of hardware architecture of what we will do with Loon as a demonstrator in 2025? To give you an idea, we are moving to the kind of schematic that we are used to in the classical world when we are doing FPGA or ASICs or this kind of stuffs. Then the complexity of the wiring in the chip is very, very, very complex. And design team, it seems that good design is making good business. At least that was Mr. Watson, one of the founders of IBM, said. That's good design, but we really begin to build this quantum computer in our Poughkeepsie offices. And to give you an idea about the timeline, we plan to demonstrate, and we have demonstrated the quantum-centric Qiskit plus HPC, and I will come back to that. We plan to demonstrate quantum advantage on some use cases next year, chemistry and maybe optimization, but on very tiny vertical. The viable path to error-corrected stuff, and to demonstrate in 2028 the first full-stack error-corrected, because maybe something that I did not say, but to create error correction systems, you need to first work on the code, QLDPC code for quantum low-density parity check, but also to work on the magic state factory, also to work on the different modules, not only the logical memory, but how to apply gates to the logical memory, etc., etc., etc. And that's a lot of work, but that's everything is on one paper, which is published, which is the architecture, and that's moved to different kind of specific paper. Then everything was published on that in June. Then last, in the 5 minutes I have, Jean-Michel. No, but I said I will say 25. The reality is that we are still there. If we map on the circuit size, the number of gates, and the circuit width, the reality is that what we see is that the hardware point of view and even our future stuff, they will not be able to address every use cases when we map with what we know of the current algorithm states. Then we need people to work on the algorithm states also. And to optimize the algorithm, the question is, how do we move this one on the left and how do we move the hardware on the right? That's pretty obvious. With groups of partners, and some of you are on these partners. That's the last numbers I updated before coming here. And I want to give you one stuff is that every summer IBM is doing a Qiskit summer school for free. And we are limited by one stuff, which is Discord. We use Discord and we are limited by the number of people on one Discord server, 8,000. The reality is that in 3 days this year, we reached the maximum number of registration. It was a surprise for us, to be very honest. But that means that there is a lot of people working on this stuff. And to give you also an idea, I think that's around 2,000 to 3,000 was coming from not Europe, but more India and or other Asian stuff. And that means that we also need to put a lot of emphasis and maybe more emphasis on software and algorithm development in Europe. We don't think, I mean, look at AI. What's make the value? Of course, NVIDIA is doing a lot of money, but AMD is also fighting them against this monopoly. But the more value is created with software. We need to put more effort on software. And why I'm saying that? Because when I look at the algorithm blue, I mean, that's something by Stephen Jordan. There is a lot of contribution, but this page is huge. In optimization, everyone talks about QAOA, but there is a lot more algorithm that we can imagine. And that will move to one stuff is that everyone was using on chemistry VQE, and we came with another method, which is called SQD for sample quantum diagonalization with our partners of RIKEN. And to give you an idea, that's once again the workflow of this morning is you prepare the digital representation, you do the samples on the quantum computer, and you do the post-processing on the GPU. It was closed with Fugaku. Fugaku is the largest HPC in Japan, owned by RIKEN. And then it gives a lot of very good, let's say, success on the usage part. That's why also we announced this partnership with AMD, I think it was 2 weeks ago or 1 week ago, which is huge. And that's also another way that we can clearly demonstrate that we are committed to open methods, because OpenCL of AMD is much more strong and open than CUDA, even if everyone on the market is using CUDA. But why using a software that is restraining you to only one kind of hardware? That's an open question. I won't do any stuff. And to give you some idea on the chemistry, that was published in Science Advance, but that's also the kind of stuff that happens with this new method, is that RIKEN was the first one to publish that. And soon after, I think a quarter after, 3 months later, Cleveland Clinic published 2 papers with the same methodology on different use cases. And Lockheed Martin applied that to other use cases. And there is other way to think of it. There is the error mitigation stuff. I think this morning we heard a little about that. That's, I mean, I'm sorry for the chart. That's a pure screenshot from LinkedIn because I didn't have time to create a chart on that because that was yesterday. I'm sorry for that. But that's a new method. That's on high energy physics. That's absolutely not on optimization. But on optimization, we also have done some work, and I know that some of you know some of my colleagues that are on this paper, and I strongly encourage you to look at the Colib library, which is called the Intractable Decathlon. That's the name of the paper, which is quite funny. They selected, and that's not IBM, that's the full people that you see on the left, T-Systems, GANs, etc., etc. They selected some very hard problem, and they reverse the problem. Rather than looking at what I wish to do, that what are the strong problems that I have difficulties to resolve with classical method today, and how can I produce classical and or quantum methods to solve these very strong problems. Then it's a public open library again. You can you can find that here. I strongly encourage you to look at that. There is the MIP instance, the Cubo instance, and there is a lot of stuff on that. You can contribute, and there are, I think that's the list of the 10s. Did I count well? Yes, that's the 10th good candidate problem to explore, because if we can solve better with classic or quantum this problem, we will have a strong advance in the market, whatever is the use case at the end. That's the theoretical problems that are used today by every people that use operational research. Saying that, we have some people that work on operational research, and I won't deep dive on that. You will have the chart, and I think that's all. And Jean-Michel, I said 20 minutes. I've done 25. I'm sorry for that. Big applause. Then, if you have any question, you can say that, and I will repeat the question for the people online. Yeah, sure. If you have any question, just yes. All to all. Yeah. First, hardware. The difficulties I don't put charts. I did not put charts on the hardware side, but clearly, even creating Iran was not easy. Iran, all the red stuff, they are coupler and specific couplers that will suppress the cross talk between qubits, and that was why we achieved that much quality of Iran, because of the fabrication processing. But moving to Loon, then having a 4 square lattice, a square lattice, and having another connectivity, a 6-way connectivity, that's the objective to apply the QLDPC code. It's very hard from an hardware standpoint. And at the end, we will be limited by the hardware fabrication capabilities. But if we think about the FTQC regime, then the lattice will be much more expressed because of your QLDP, of your correction code. And then it depends of the correction code, and then the correction code depends also on the hardware. And there is a kind of cycling on that. Because it's a trade-off. Everything on quantum computing is a trade-off between that. I think I put the chart, yes. It's a trade-off of that. Let's forget speed, but it's a trade-off between scale and quality and fabrication capabilities. Then you want to maintain the best scale. That means having qubits, and as soon as you masterize your qubits, you can imagine to have better lattice and to diminish to increase the number of connections for each qubit. But that was one of the issues, and you can see the differences. And if you remember, before Falcon, the early birds, the little birds, were not with this kind of lattice. We moved to this hexagonal lattice with Falcon because it was easy for us to produce while maintaining a good quality and have the capabilities to scale. And I think we demonstrate the scale. With this one, it was easy to demonstrate the scale. And clearly with Iran, we increased the quality while diminishing the scale. And Nighthawk, the square connectivity, would be a way to increase the scale while maintaining the quality and the fabrication processing. I don't know if it's answer clearly your question. I don't know everything on fabrication because that's one of the best secrets of IBM that I don't know, to be very honest. The last one. I killed everyone. Eric, yes. Yeah. Yes. Yes, in global. And then that's why we also do a lot of work on the software side on the speed. And the majority of the software speed on the speed acceleration is done by the optimization of the control code. Not the error correction code, but the way we control the qubit and I mean, we use FPGA, and the way we implement the control of our qubits inside as a software. It is a hard-coded software, but still software. And another way is that we don't. I mean, I'm not sure of the answer I'm giving you, but I think we don't see an issue from a speed point of view related to the connection of the couplers. It doesn't impact us too much on that. The main question on the coupling is, can we maintain the quality, and can we have the quality enough from a coupling standpoint to be able to scale with the multiple chip and multiple memory and then error corrected modules. But I'm not an expert on that, and maybe I said something terrible, and I apologize for my colleagues. Yes, I'm there, and I'm leaving tomorrow morning. I'm sorry for that. I apologize for all the speakers I will miss.